Hello YouTube! In this quick video we are going to discuss the 3 laws of motion that Newton proposed. The first law is actually quite easy. It just says that if the force is equal to 0, there's only going to be a constant linear velocity. So you're always going to move in the same direction with the same constant speed. So you actually have this formula right here for constant velocity, which is just our x-coordinate is given by our v0 times t plus our x0. This first law also means that the acceleration has to be 0, because if there were any acceleration, this integral right here would depend on the time and our velocity could not be constant anymore. The first law is often also called law of inertia because it says that every object has some inertia that it doesn't move its velocity from its own. So it's inert to keep its velocity. So the second law is the actual action principle, because we have not discussed what the force actually is. We just have discussed that if it's 0, there's a constant velocity. But what is a force actually? And the second law, the action principle, tells us what a force is. And it says a force is what creates an acceleration. And acceleration is always caused by some form of force. So force causes acceleration or a change in the velocity vector. And don't misunderstand me. The change in the velocity vector can mean both acceleration, deceleration, and or direction. So it can also change the direction and the speed. So both are possible. You can go faster, you can go slower, but you can also change the direction through your force. So if we look at it, actually we have some kind of ball right here, and this ball has some some white velocity, and it also has a friction force applied to it. So it's slowly going to lose its velocity because the friction is actually opposite to the velocity. Now up here we have, very interestingly, we have a planet or something that's orbiting something, and it's on this circular path. And there's actually a centripetal force that's actually pulling it to the center. But this object is not getting faster or slower, it's just changing its direction. And we're going to see that you can split every force into a part that goes parallel or anti-parallel, like this force right here, and a part that goes orthogonal or perpendicular to our velocity, and that causes a change in direction. So we're going to see that that's always possible in the next video. Right now we're going to have a look at the third law of motion, which is the principle of actio and reactio, or as you would say, action and reaction. To every single force there's an equal and opposite counterforce. So each and every force has a counterforce with which it would be equal to 0. Sum both forces up and you would get 0. Now don't misunderstand me. That does not mean that every force has to be 0. That's nonsense. It just says that there is somewhere in the universe an opposite force. We don't know where, we don't know what it does, but it's there. A good example is the Earth and a ball on top of the Earth. So right here I have a ball that's falling down, and the Earth that's actually falling to the ball, because the ball has a force m times g. We've seen that once. The g is the Earth acceleration, and m times g, as the formula goes, is m times a is a force, so m times g has to be a force. So m times g is our force with which this ball is being accelerated. M times g has also to be the force with which the Earth is accelerated towards this ball. Now the ball still experiences a force, because the force is not 0. They are not both at the same position. The ball and the force are not at the same position. It's not like this. The other force is actually down here. And there's another thing. Both objects have a different mass actually. So if you want to calculate how fast they're going or how fast they're accelerating, we can do that by dividing our force through our acceleration, through our mass, by dividing our force through our mass, and then we get the acceleration. Now you could say, I don't feel the earth coming towards me when I jump. That's actually nonsense. But I'm going to show you that it's actually there. You just can't see it. You can see the 9.81 meters per second squared, that's the gravitational acceleration on the surface of the earth, but you can't feel or see the 0.0000000000000000000164 meters per second squared. That's 1.64 times 10 to the power of negative 23 meters per second squared. The acceleration is actually so low that we just can't see it, we can't experience it. And that's why we always think that, oh, there's only one force, but there's actually always two forces, one actual and one reactual, one action and one reaction. There's one more thing though. I have to admit to you that I actually lied to you. I've actually lied to you about this force actually being a scalar. It's actually a vector, and each of these laws is actually formulated with vectors. So everything that I told you about was actually formulated for vectors. So there's actually no scalar right here except for time, like dt or this t right here, and mass. Mass and time are the only two scalars in this whole thing. So we actually formulate all of this for vectors. What does it mean? Well, actually it means about nothing in most of our calculations. In most of our calculation we actually take the absolute of the vector, so we really don't care about its direction. But in some cases the direction is important. When is it important? For example, if we force this rotation right here. And don't worry, we are going to talk about rotation and translation some more, so there's quite much to keep in touch with. But in the next video we actually want to talk about how we deal with these vectors, because these vectors seem quite difficult. How do I deal with them? And I already told you, or at least a bit, that if you have an object and it has some velocity and it has some force applied to it, that you can actually divide this force into its components. So one component going parallel to this velocity and one component being perpendicular to it. And this one component is actually going to change the direction, and this one component is actually just going to change the speed. But we're not only going to talk about dividing forces, but we're also going to talk about adding forces. So we have an object here, and there are actually two forces applied to it, like this one here and this one here. What is the resulting force? And we're going to see that the resulting force looks somewhat like this. Both things are quite important and quite common in physics, so please join me in the next video. I hope I'm going to see you next time. Goodbye, have fun. Tschüss.